Okay, shall we start? So Zafira-san, do you have anything you can show me today?
Hello? Hello?
Okay. Yeah.
Okay. So I draw some picture for the rotary diffraction damper so we can show to the company. So basically we have two rotation at the side and viscoelastic at the middle. And then this is a plan view and this is the deformation after lateral force. So basically it rotates this way and the other one like this, and one viscoelastic go up and another one go down. So this is much more clear view to see.
But I think the left part and right part must be overlapped. And viscoelastic damper will be in the middle.
Yes, the viscoelastic is here. Okay. This is the layer of viscoelastic here. One, two.
Okay.
Yeah. So when it deforms, the shadow, you can see the shadow. The shadow is viscoelastic, so the shadow is viscoelastic deformation. And this is 1, 2, 3 is the steel plate.
What will happen in the middle?
In the middle?
Yeah.
Viscoelastic will deform. The middle, this is only the middle plate.
Middle plate? Could you show me section again?
Here.
So viscoelastic is where?
Here. Can you?
Here? But only this part is only viscoelastic?
No, not that one. This one, Sensei. This one. 1, 2, 3, 4.
And what is the middle?
This is steel plate. Steel plate.
Steel plate.
Steel plate, yes. Because viscoelastic damper is sandwiched between steel plate and viscoelastic material. Yeah.
Is this the same as the layout of reference? There is a yellow reference of viscoelastic damper.
So I will open one. So this is deformation, one of example deformation of viscoelastic. And this is the viscoelastic. So it's a layer between steel plate and viscoelastic material.
Could you magnify this section?
This one? The yellow color?
Yeah. So how it is sandwiched?
Sandwich? So if you can see the black color here is the viscoelastic and the yellow is the steel plate.
So there are so many plates.
Yes. Layers, yes.
How many layers here?
I think 17.
17.
Yes.
But in your case, only 2 layers.
Only 2 layers.
Why?
This capacity is much more bigger than the one in this one.
So how do you increase cap layers in this case?
We can add more steel plate and this become thicker. At this side also become thicker. Maybe I can draw some. So for example, if you want thicker plate, then we can just increase. So the middle part is steel plate. So we can just increase the number of this here. So this is the steel plate. For example, we want layers, another layer.
So middle steel plate you are now checking. It's not connected to.
No,
Right.
it's not connected.
Why?
It's connected by the glue with the between the viscoelastic material, isn't it?
Could you make viscoelastic material, I mean thickness more thicker than this one? I don't know where the viscoelastic material.
You cannot see.
Is it so thin?
It's 5 mm supposedly. For example.
Mhm.
And then this one continue combine and only steel plate sandwich in the middle.
Oh,
And
really? But so only steel plate connecting, I mean, beam end is only top and bottom, only 2 plates.
Should be yes. Or
Mm.
we have to connect it, everything here together.
So which one is, I mean, same as reference?
Same as reference.
Mm.
This one only four layers, and this is based on reference. So if what do you mean is this one is friction damper, means that the steel plate here can also connected to the rotational damper, friction damper. So we can put like this and here. And this steel plate connected to viscoelastic. Is that one is better?
Sensei, Zafir-san, may I show my proposal for this number?
You can show it.
Thanks.
Mm-hmm. Oh, Ahmed-san, I cannot hear your voice.
Sorry. Yes, Sensei and Zafir-san. I tried to add the I-beam section to the proposed number.
Mm.
I connected the beam section with the rotational friction disk, and then tried to overlap between the right side and left side between using the viscoelastic number.
Mm. Yeah, this one is, I mean, reasonable. Yeah.
And maybe it's more clear. Yeah.
Mm. But still, how to say, friction damper right side and left side is not symmetry. I mean,
Symmetric.
Mm.
Yeah, I tried to make it symmetric, but for overlapping, I think it's hard for them to be symmetric.
Mm. Mm. Yeah, so we must think about how to do it.
For being symmetric, yes, I think.
Yeah. Yeah. Yeah, this is I think one idea. Another idea might be we can put some. Ahmed-san, could you keep your picture?
Yes, it's true.
So one idea we can separate, I mean, viscoelastic part, and viscoelastic part is up to here, and directly connecting middle plate in the middle, and the friction part is left and right. So how to say? なんだろうな。So viscoelastic part and friction part. It's not the same plate. It is separated by vertical, how to say, vertical plate. You understand?
I understand.
Mm.
I understand.
But I don't know how to do it. Well, but yeah, Ahmed-san's one is, I think could be, yeah. Zafira-san, could you show me the reference viscoelastic damper, yellow one again?
Okay.
Ahmed-san, could you close your
Yes,
window? So let's see.
So we put the plate here, and then one plate here.
Yeah. But one moment. I just want to know this one, right side and left side. I mean thickness of beam. I mean, this one is thicker than this one.
No, it's the same.
Same? How
Yes.
you can make it same?
How it's same? Let me find the drawing.
Yeah.
I think I have inside here previous. Okay. Viscoelastic. And
Do you have another detail about
in the book, yes. They have section properties.
Do you mean the thickness of friction materials inside?
No, the viscoelastic.
Viscoelastic damper? There is a reference of yellow colored viscoelastic damper, and viscoelastic material is sandwiched by steel plates. So I want to know the right side and the left side of the beam. I mean, which steel plate is thicker than the other one? I mean, total number.
Yeah.
No, not this one. 待てよ。
This one.
If you go to, could you go to up?
Up?
Up left. No, go down. Yeah,
This one?
This one. Concept 1, 2, 3.
Yes.
Concept 1, what is? So left side is only 1, 2, 3, 4 plates. And right side is 5 plates or 6 plates?
5 plates.
Maybe, no, 2 plates more. What? 5?
1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is 1, 2, 3, 4. 1, 2, 3, 4.
1, 5. But 1 plate more in front and the back side, no?
Yeah, this one and this one.
So it looks 6 plates, no? But
no, it's 5.
Why?
5. This is 4.
So,
the viscoelastic material is 6. 1, 2, 3, 4, 5, 6, 7, 8. No, 8. It have 8.
Is there any drawing from, I mean,
From the thesis?
From the top?
From the top.
Yeah.
This one.
Okay. Could you magnify? Could you magnify more?
More.
Okay. So if you look upper one, this is connecting from the left side up to here, right? And okay, right beam is coming from left to right to left. Okay. So total number of steel are same, left and right.
Yes.
But there's a how to say, kind of ギャップね。
うん。
And, there are many layers in the middle,
うん。
but both end, how many layers?
Both end?
What is this part? This part.
This is also stiplet from here. Stiplet. And this one.
Okay. Are you sure?
Yes.
Are you sure?
I think they like welded together, like become one like thicker plate.
Okay. There is a plate, I mean, sandwich it. And if the plate is head is here, this one is coming from right to left, connecting. なんていうのかな。I don't know how to say. ちょっと待ってよ。Can I share my screen?
Yes. Yes.
Can you see my handwriting?
Yes.
待てよ。No. あれ handwriting. ダメだ。まあいいや。Okay, so, okay, so this plate, starting from, let's see, here. Okay?
Yes.
Yeah.
Yes.
And then this one is coming here, right?
Yes.
And also this one coming here, maybe. And on the other hand, this one is coming from here, right?
Yes.
And this one also coming from here. Okay. So, Zavira-san, your drawing is like a plate is sandwich in the middle, and only upper part and lower part is connecting to,
The
end of
rotation.
but it looks all plate is connecting, end of the beam, and in the middle part it is somehow, how to say, overlapping.
Okay.
And some things I don't know for sure. This one looks stopping by here, right?
Yes.
So there is a case plate is not connecting to end.
Mm.
So it is not so clear, but so anyway,
先生、
Hmm?
I think if we see it from the elevation view,
Uh-huh.
maybe I can show. So here is the elevation view. So it means that this is I-beam. This is it looks like I-beam. And then it stick together in between. I think the steel plate is only until here. Here. The steel plate is only until here. Here. And then this is the I-beam. This one and this one is this one. So all the steel plate that sandwiched with viscoelastic is only this part and connected to the bone.
So what is the dotted line?
Dotted line? This one?
Yeah.
The dotted lines mean is invisible. It's behind this flange. Behind this flange. This one is this plate. The flange. The web. The web of this I-beam. This one.
I-beam.
Yeah, this is I-beam.
Are you sure? So this is I-beam means only one wave and
Yes, one web.
really, but there are dotted.
Yeah, this is one web here. Can you see? Yeah.
I don't think so. There are two.
This two dotted line, but it's defined as the thickness of the web.
Why?
Why?
Could you magnify this picture?
Yeah. I cannot move this. Okay.
Could you magnify?
Yeah.
Yeah.
So this is I section.
Could you go down? Yeah. Could you go down? Yeah. Stop.
Yeah.
There are this one and this one and this one. There are three plates at least, and two of them is continuous to. So it's not I plate. There are two plates here.
This is plate from the sandwich. And then it's bolted to this I plate. This is the I plate here. And then this plate is connected to this end.
Oh, okay.
Yeah, this is also one I plate. And then this steel and this one is connected inside this. So, and then everything is bolted with the bolt.
What is the middle part?
Middle part?
Yeah.
This one?
Yeah.
I think this is spacer. This is filler. If you can see the written here.
Yeah. What kind of section?
This one, filler PL22. This one. It's a filler for fill the gap between the plate.
But how they fill the gap?
It can be put as a steel plate. Not. Was it? We can use another steel plate to get as a filler. Filler PL22.
How filler is arranged in here? I can read filler. It is written filler, but I don't know how it is arranged. So could you, I mean,
Yes.
think more
About how to do.
precisely? Yeah, how do you make a specimen?
Okay.
Mm,
I will check what kind of filler they use.
mm.
Okay. And then I also check how to design the friction damper. So this is one paper that explain about rotary damper, but this is different application. This is in frame, but for our study we only use a beam. So it's very simple for the Fy times the length of coupling beam divided by 2. And then we can estimate the moment 255 based on the estimate force we want to restrain. And then after that, we can use this formula, My equal to this. So basically this one, the damper moment capacity design. So we can use this formula to calculate how much the capacity based on the estimation of the force. And then there's another one proposal that I found. They use spring in between the rotary friction damper to increase the stiffness and also can dissipate more energy compared to normal rotary friction damper.
Mm. Oh, this is interesting. Mm.
And I also did try to find the limit for the displacement-based design based on the book. So basically, they find the way they find the degree of coupling is based on the moment of overturning resistance, and this is the formula. So for the building, I calculate there's two type of model. One is 3.5, the longer beam, and another one is a shorter beam with 1.25 coupling beams. So we can see the shorter coupling beam have higher degree of coupling based compared to the longer beam. And after that, we have to find the contraflexure height based on the book recommend this graph. So basically, we determine the degree of coupling beta f. So it's around 0. For example, this one is 58%, so 0.58 here, and it's around 18 story from here, and then we can get the ratio of the contraflexure height is 0.6, and then we can determine the contraflexure height. And after that, we can, in this book, they recommend 2%. And it explained here in this reference, it said 0.5% plot described as elastic and or pre-yield. And between 1 to 1.5 is significant global yielding. But if it's over 2.5, the global drift is still within the inelastic range. So I think that's why it takes between 1.5 and 2.5, which is 2% for this study.
So you explained two things. One is the degree of coupling.
Mm.
And could you go back to the formula of degree of coupling? This one.
One.
And yeah, I know this formula.
Yes.
But this moment, how did you get this moment?
Which moment is it? This one?
Yeah, I mean the next slide.
This one.
Yeah. How did you,
The shear force in the beam
yeah.
times the length between the center of the wall to the center of here, the center of the coupling beam.
Oh, you get this. How about moment? M1 and M2.
M1 and M2 is the bottom moment of the wall.
Under which lateral load?
Which lateral load? In this study, this one is based on in 1/250 pushover.
Okay.
Yeah.
1 over 250 pushover. So if
This
you push more, degree of coupling may change, right?
Actually, sensei, here it says the capacity of the beam itself. So overturning resistance by the coupling beam. So I took the shear force based on the capacity of the coupling beam.
Oh, sorry, I don't understand. What capacity coupling beam? So you are talking about the pitch value.
So, but I can show. So, for this is from data beam, and this is from data wall. So based on here, I can determine the capacity of the wall and capacity of the beam. And from here, I calculate TL, and then this is degree of the total of shear and length between these two. Because it said here in the it said the overturning resisted by coupling beam. So it means the capacity of the beam.
Capacity of the beam, well, how to say? Capacity means yielding capacity. But so why you use yielding capacity? So first you push the building.
Yeah.
For example, 1 over, let's say,
1 over
1,000.
200.
No, 1 over 1,000, for example. Deformation.
Yes.
So no member is yielding.
Yes.
But you can calculate degree of coupling by this formula. Right?
Yes, but the degree, if the force is small, the degree of coupling also small.
Why?
On the beam.
Why degree of coupling is small?
So for example, this is 1 over 250. And then this is the force from the coupling beam. This is your force here. And then if I calculate the OC,
What is the shear force?
shear force here, from here.
Okay.
So shear force is the total times by L, the length between here and here. So for
Coupling. Mm. So this is a result of 1/250.
Yes.
And if you push 1/1000, for example, share force will be smaller.
Yes. Yes.
And also moment is smaller.
Yes.
So degree of coupling may not change so much.
Okay, I will check with the lower pushover and compare to 1/250 and also 100 or 1/50, 2%.
Mm. Okay. Yeah.
Yeah.
Mm.
So, yeah, that's all, Sensei. And can you help us to explain about the viscoelastic the programming?
Mm-hmm.
Can you help us to explain? I sent you email about a few questions regarding the programming.
Yeah.
Okay.
But I how to say? I sent you just example by Fortran, so you don't need to なんていうのかな。exactly follow. Ahmed san, how's your situation about the Python code? You're working independently with Zafira san, or you're discussing each other?
No, I'm working separately, but for me, I still have errors in my code. After combining, just after combining, I can display the hysteresis for each one separately, but after combining, still have errors. So just I'm still trying to just to fix the errors. Yeah.
Yeah, Zafira san, could you talk with Ahmed san? And maybe you can how to say discuss how to develop Python code.
Okay.
Yeah. Yeah. アハメドさん, can you show me the Python code now? Or do you think it's better to be next time?
I have situation which I can share my screen.
Yeah.
Just realizing something.
Mm.
I just for me, I try to I work on the Anaconda because it helps me with coding. But for this code, I still have some errors with the code, so I just need to modify this code. Yeah.
So,
I just
how to say? Last time you made a code for viscoelastic only,
yes, Sensei.
and you modify the previous code combining bilinear.
Yes.
Right?
I tried to get the help from the Fortune sample that you sent us last time, but it didn't work. So I just need more time just to find the errors, and I'll try to fix it. Yeah.
Yeah. Okay, Zafira-san, I think Ahmed-san also try same thing. And it looks his approach is okay. So yeah, maybe it's better to work together. And Ahmad-san, could please explain Zafira-san, I mean, every line, one by one.
Okay, what I did.
Yeah.
Okay, Sensei.
Zafira-san, okay?
You can explain, Ahmad.
Okay, so let's see. And also, please think about how to design. I mean, viscoelastic damper with rotational friction. Okay. Anything else?
Sensei, about the friction damper, rotation damper, I'll show you how it to design already. Maybe I can show it again if you don't understand. Ahmad, can I share my screen? So,
Yes.
so basically in a rotational damper, we call clamping force here. So, and also we have the friction surface. So we have internal radius and outer radius. And this is the formula that they use. So based on the clamping force, it's also the clamping force is how tight we bolt into between the plate, the rotational plate. So we only, for this one, because it's a very small capacity that we want, so we only need one phase. And then the clamp force is about 70 kilonewton. And then from here, we can calculate the moment capacity of the frictions.
So how did you get this MY?
MY, this one?
This formula?
This formula is from this book. This paper. From here. So in this paper, they use this kind of in between the frame. It's like a hinge. So from here, they calculate. Here. The design them for using this.
Yeah. But how do you derive this formula?
Derivation from here.
Really?
This is MY. And then this is the push stiffness.
No. Could you go up?
Go up.
Go up. Go up. Go up. Yeah, stop.
This one.
Yeah, this one. Yeah.
Yes.
So they calculate okay, small area. And NQ. What is NQ?
And
You calculate the friction force, I think, for surface area for a small part, then integrated it for the whole disk.
Mm.
And it's the number of the phase, the friction phase, number of introduced, and Q is the clamping force.
Okay. Mm. Mm. Okay. Mm. Okay. Yeah. So, Zabura-san, you must understand completely the theory behind. So
Okay.
don't believe the equation.
Okay.
You must start from figure 3
Figure 3.
and derive the, I mean, this moment is a moment of where?
Moment of where? It's in the middle here. I think it's two different moments. One is a design moment, another one is moment from the calculation itself, from the structure.
So this moment represent, I mean, rotational force.
Yes, in the structure. So if you see the flow of the design. So first in here, in this part, they calculate the my based on the structure itself, based on the eccentricity and everything. And then after that, they design the damper itself by using this formula.
Okay, so could you go up to equation 7?
7.
Yeah. So next time, please explain the meaning of equation 7.
Okay.
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 And we don't know what kind of rotational damper we will use.
Okay.
It's up to Sumitomo Riko company.
Okay.
So next week we will have a meeting, Sumitomo Riko, at 11 o'clock, 24. So please join the meeting, and we will discuss what kind of friction damper. And you can show the, I mean, paper you found today.
Okay.
And I will ask their opinion.
Okay, Sensei.
Okay, so Ataya-san, is it okay, Zafira-san and Hamed-san?
I'm finished, Sensei.
Ahmed-san, are you okay?
Yes, Sensei.
So, Ataya-san,
Yes, Sensei.
your turn.
Since I sent the manuscript today in the morning by email.
Oh, yeah, I received. Could you explain where did you change?
Okay, Sensei. Since I modified this part.
Yeah.
I explained that this single TMD scenarios are 3 separate scenarios. Each has 3% mass ratio.
Okay.
But this is only one scenario composing of 3 TMDs, which has a 1% mass ratio. Total mass ratio is 3%, as the same as single TMD mass ratio.
Okay. And why, how to say, MTMD, there are on the top.
because all of them is shown to first mode of the building. You can say.
But it looks middle one is small.
But the weight is because the span of the plan is different, but the weight is the same. You can say. The mass is the same.
Mass is the same.
Yes. You can say.
Okay.
Indicate which case the TMZ can say are indicated.
Yeah. Okay, fine. Yeah.
This section is not necessary or deleted,
Yeah.
and this can say it's because of this three figure of rhythm in X direction and up and down. But I changed a little. I created another section, selected the motion record. This for detail about this for it.
Okay.
And created the acceleration response spectrum for both directions, distance and up down. So here I state that these structures are characterized by restricted movement along the horizontal y direction. Consequently, only the space and up-down components of the GMRS are applied to obtain dynamic response characteristic of the buildings under consideration.
Okay.
Yeah, because of this.
Okay. Yeah. Okay. Fine.
So I deleted this section. And please make one scenario to explain, one section to explain input. So this is that section.
Okay.
And also I indicated the TMD for the second model also.
Okay. Yeah.
The reference number, I also inserted the reference number simply for the NatHaz online wind simulator. And that's all, simply.
Okay, good.
Yeah, and I already sent it today in the morning.
Okay, I will submit this one to the editor of the journal, and yeah. If they accept, we can submit it for free of charge.
Okay, thank you very much.
Okay, good work. So shall we decide the next meeting? So next meeting will be one moment. So today is 15. So 24, we have a meeting with Sumito Moriko from 11 o'clock. And どうしようかな。そうだ。How about the 31st of January? 3 o'clock afternoon.
I'm okay, Sensei.
Ahmed-san, are you?
Yes, yes. Okay, Sensei.
Ataya-san, how about you?
Okay, Sensei.
Okay. So next control group meeting will be 31st, 3 o'clock afternoon. Okay. So shall we finish? Okay.
Bye.
Bye-bye.
Thank you,
Yes, ma'am.
Sensei.